Yeah.
16 miles.
How long did it take? When I
Okay, gallery view. Hey, there we go.
Evening, Tom.
Good evening, David. And all the Zoomers at sea. We're still loading stuff and getting ready, but chillax, have a beer or your libation of choice, and we will get around to you all. I guess we're back to recording. How do I pause the recording in progress now? So would you like to start over?
I was going to say, shall we go back to the beginning and do a treasurer's report?
It's in the minutes. It's all in the minutes.
It's all, yeah, it'll be in the minutes, yeah.
And the website's there, so you can get to it and you can see it all. And that's really the big thing, is we wanted to show that the website is functional. And I'm still doing some updates. I'll get back to home here. Still doing some updates, but once we get settled down on our meeting location, that'll be updated too. I want to confirm something, and I'll get that updated. Under the email discussion lists, we have SAC announce with a note that it may be obsolete. I'm thinking the SAC announce is no longer used. Is that correct? Anybody know?
Probably correct.
Because we're using the AZ observing, right?
Right.
And I don't know about SAC forum or SAC board. AZ observing is here, so it's in there, how to get in and out of it. But I'll take the SAC announce out. Does anyone know about the SAC forum or SAC board?
We don't use the SAC board, but I think the SAC forum might be used very rarely.
Okay, well, we'll find out. I'll do some
But,
testing on that and send some test messages and see what goes out.
In other
Hey,
words,
anybody-
SAC observing is for all the clubs, but SAC forum is just for SAC.
Right. Well,
or
that
who
was
it relates to.
the idea.
Yeah.
They all
Anybody tuned into, excuse me, anybody tuned into the meeting that is using that or any of those, please let David know, because all of that's foreign to me.
I'm
Other
on those three lists, and I haven't seen anything posted to those in probably well over a year.
Yeah, me neither.
What I'll do is I'll just currently take those listings off. We can always put them back on, and we'll see where we go from there. But the AZ observing is still very current and still being used. If anyone's looking for observing lists, we do have quite a few of them on the site, and they are downloadable. So if someone's not sure of where the site is, basically all you do is go to saguaroastro.org and you'll find us. Now, someone's going to forget that because they're going to think it's Saguaro Astronomy Club, because that's what we show. So if you forget, you can just Google search for Saguaro Astronomy Club. It will come up that way and it'll get you to our site.
Well, David, this evening, we actually have someone speaking about the observing lists.
Very good.
You'll hear that if you stay tuned.
Okay. Now, you say you want me to go ahead and go into the thing we talked about, or shall I save that for later if there's time?
I would go ahead and just do it.
Going ahead to do it. Everyone's going, what's he talking about?
They'll find out.
They're gonna find out.
It's not in a bad way.
I have been doing something lately. That's not a surprise for those that know me. But anyway, what I'm going to do is get here to this is my web page, and everything I'm showing you is on the web page. And I had proposed doing a little talk with the subject being looking for some galaxies. Now, I think most of everyone here probably knows what a galaxy looks like, but we'll just have a quick look because I'm going to show you some contrasts. Everyone should be familiar with, for example, M51, the Whirlpool galaxy. We're used to large identifiable objects, which are beautiful to look at. And by the way, all the pictures that I'll be showing you here, I have taken here from my backyard in beautiful light polluted Tempe.
Wow.
Or I might have some of the older ones out at the antenna sites, but most of them, probably 90% or more, are right here from the backyard. I have an observatory in the backyard. Anyway, there's a galaxy, no question about it. Now that's a nice bright one. Oh, did I hear a question? No. Okay. M101 presents a slightly different kind of galaxy, one that we're used to seeing, a dimmer one and a spiral. This is the kind of object that people are used to seeing or wanting to see if they look at galaxies. But I'm looking for some other kind of galaxies. And what I'm into is a thing called Abell galaxy clusters. Now, the Abell galaxy clusters, they're a bit unusual. Abell, by definition, wants at least, and by the way, they're relatively new. It's not an old list, but they're relatively new. Abell had some requirements. I won't go through all of them, but the thing is, there had to be at least 30 galaxies in the cluster, and it's a definition of, he has a definition of how he puts that together. What I'm going to try to do tonight is just give you an overview of what I've been looking at. And if we stir up any interest, I can do a detailed presentation on it later on. I'm going to show you an idea of one though here. Abell 1060. I am going to need to narrow my screen down just a little so I can maneuver. Okay. On the EVAC list, I'm looking for Abell 1060, and it's one of the big ones. Right here. Okay, now this is going to be my image, unannotated, just what an image would look like. And there you go. There's at least 30 galaxies. Everyone see at least 30 galaxies there? I hear you. I hear you laughing. You can't get away, even though I'm not there. Yes, there are at least 30. As a matter of fact, there's over 175 galaxies in that picture. Now you might start to get an idea of what I'm trying to do. Abell was looking for distant clusters. Now I'm going to go back on this. And I also have these. With a little luck, I'll click right here. I also have these on AstroBin. And one of the nice things about AstroBin is annotation. So this is that same identical image where you're looking. Now you can see some of the galaxies right there in the center, little tiny little buggers, and they're in different parts of the screen. But here's the fun part. If I move my mouse over onto the image, the red markings from the annotation are things that we normally think about, like NGC and IC objects, normally the larger objects, although these are small within themselves. But the blue circles are, each one is a separate galaxy. They're dim, they're far, far away. And they are all identified and plate solved with a PGC designation. So when I said that there was over 150 galaxies in that image, there you go. There's over 150 galaxies in front of you there. This, by the way, the magnitude for an Able galaxy cluster is the magnitude based upon the 10th brightest galaxy in the cluster. The actual measured number of galaxies that are in this cluster for the Able designation is 50. The other 100 that are present are not part of the Able cluster, but are just there in the field of view. I was going to show just a couple more to give you another flavor of what I'm searching for. Here's an image for Able 4038. Now, something that might be of interest, I show two different designations for each one of these. One is AGC and the other is ACO. If you're using the SIMBAD, you'll use ACO. If you use the SkyX, which I do, you'll use AGC. This is 4038. How many galaxies do you think might be in there? Well, here's a quick clue right here. What does that number say, Tom? Right here.
About 317, yeah.
Yeah, a little more than the last one. Now I'll back up on that, and I'm going to look at 4038 on this sheet. I can go over here, and this is again the view. How's that for a cluster? It's almost hard to find any miscellaneous stars in the group because the screen's filled up with, there's over 300 galaxies in that field of view. Now, by the way, I can take these images and I can zoom in on them. You zoom in or zoom out. I can make it bigger, okay? And in each one of those circles, there is, there's something there. Well, what that something is a galaxy. It may be a very, very dim dot, but nonetheless, it's an identified and recognized galaxy. And that's the point. We're looking for clusters of galaxies in the distant view. The magnitude for 4038, by the way, is a mag 14. Now, what do I derive from that? What am I trying to say? If you look for it visually, you may have some difficulty, especially in the city. This image was taken from within the city. If you have a really big scope, with lots of aperture, you'll get a pretty good view. But the camera is a wonderful thing. It collects light over a period of time. The actual Able cluster here is 117 galaxies. The other roughly 200 are just friends and acquaintances in the area, but not part of the official cluster. Going to show also Able 1656. Here is the basic image. Hard to think of it. Now, the last one we looked at had 300 and some odd galaxies. Okay, if you have a look right here in the lower corner, I'm telling you there's 450 galaxies in this image. That's just a couple. What's that going to look like when I get them all together on one screen? I'm looking for 1656, and I go here, and I come up to the view, click on it, goes large. How's that for a couple of galaxies in the field of view?
Good Lord.
Can you read those, Tom?
I'm lucky I could read the stuff on the chart.
Anyway, there's a few galaxies in that field of view. There's a few NGCs, a few ICs, and a whole ton of PGCs. So this is what the idea is when you're looking for Able galaxy clusters, you're looking for tiny, very, very dim things. This is a mag 13.5. Now, these originally were coming off of a list that, one more back on my website. This is the Able galaxy clusters. Got to mention EVAC. EVAC has an observing program for the Able galaxy clusters, which look at the brightest 33 objects. And that's where I'm drawing that from. I'm looking through group 4. I've already done 0, 1, 2, and 3. That's mag 12.5 down to mag 15.6. Those groups are complete. I'm currently working on group 4. Now, group 4 gets down to magnitude 15.7 to 16.4. Remember, that's the 10th largest. I'm only going to bore you with 2 more pictures, and we'll see where the interest goes from there for a possible later presentation. But 1651 here, if I look at the base image, it's kind of interesting because I got an extra on this one. I'm looking for my galaxy clusters, and lo and behold, I got a double in there. And this is with the 80 millimeter at low mag, and I was kind of really surprised. I do double stars too, and that's one I was looking for, and I've added it to my list now, and it was a clean separation. So yay team, we got a double. Okay, so here we have 163 galaxies. I'll back up and say, okay, now I want to see that annotated. Someday I'll figure out how to do the annotation of my own images and not have to go to the alternate sites, but it's available. So there we are. So this is the image, and that's 163. One last image to show you how this can be exciting and finding so many galaxies. Exciting for me anyway. 1399. I'm just going to go straight to the website and say there it is. Lots and lots of little blue circles, and that gives us lots of galaxies in the field of view. Not looking like looking at M51, which is really big and beautiful, and that's what people like to see. This is in search of distant, dim, tiny galaxies, which are plate solvable and verifiable. And with that, that's my presentation, what I was going to do. And if there's any interest in this, I'll be glad to do a longer presentation on the concept and more information about the Abels if there's interest. Okay, now with a little luck, I've got to, I think I just goofed. Screen sharing. This is where we're here, right? Stop the share.
Okay.
I think I did it.
You have a question from Bob Buckheim. He says, hi, Dave. Do you remember how Abel decided that the fuzzy spots were galaxies versus something else, unresolved star clusters, nebulae that also look like fuzzy spots?
That's a piece of information I do not have, but now I know the question, so I'll have to find the answer to that. One of the interesting things on the Abels is I said there's at least 30 and as many as like 300-400 galaxies in the clusters. There is no official list on any of them for what all the actual galaxies are. I have definitions of how it would fit the curve, but no list. And the magnitude is based upon the 10th brightest galaxy in the group. But nowhere does it ever identify which the brightest one is. I don't know how you do that. I've been in discussions with acquaintances up at Lowell Observatory, asking questions about that, and they just giggle and laugh with me and say, well, that's Abel. So I guess if you're a professional astronomer and want to make your list, you can set up your own rules. But it's a fun project, and I'm enjoying it.
Well,
okay.
As a coincidence, I was having a slow day the other day, and I forget where I'd come across the Abel list, or not the Abel list, yeah, I guess it was the Abel list, and I was wanting to see which ones I had already logged. So yeah, I went through my notes and my spreadsheets that I keep for my observing, and I can get with my DSLR on maxing out the ISO down to 13, sometimes 14, if I'm really tracking well, without using an auto guide or anything. So but it's just a fuzzy spot then. But it's always fun to just see what you can log.
From
Until
here
you log them all, and then you go back and then you do better work.
From here in the backyard, the group 4 goes down to mag 16.4. And by definition, the group goes two counts above that, which means it'll reach out to 18.4. I can resolve them with my 80 millimeter from the backyard. And I can see them in the image, and it's plate solved. So I'm pretty happy with that. I don't think I can get beyond that. And there's only about 3,000 of them that are beyond that. So I won't be able to get those. Thank you.
We thank you. Okay. And yeah, we would probably in the future like to have a little more on this, how you're doing it, and because it is always interesting. And
It will-
aperture lost, and then for some of the others, your technical aspects of it. Yes.
How are you figuring out whether the galaxies are in the cluster or just lingering behind?
Pardon me?
How are you finding out whether the galaxy is really in that cluster? Because you're saying you have 150 to 300 galaxies in a picture.
There is a definition called the Abel radius. And NASA actually got involved in calculating and defining the radius for the Abel galaxy clusters. And I won't go into the math of it. That's something we can include in a later discussion. But you're looking for the brighter, you're looking for the there's a definition of the brightness and the galaxies within that radius, and radius as in a circle. So it's not the field of view. They give you the radius, which would be half. The radius, and then the magnitude is the range of the 10th brightest. We don't know what the brightest is, but figure that plus 2, and you basically start counting the galaxies. I've actually started once taking an Abel, which only had like about 40 galaxies in it. And the PGCs in the plate solve are there. I can read them. And you can look them up and you can determine the magnitude to see if it fits. And the one I was working with, it works out. You get right close to where you're supposed to be. So Abel's definition, although he just looked at all of his discovery is based upon the Palomar plates, the digital sky surveys from the 1940s and 50s. That's where he did his work from. But he just looked at it and said, oh yeah, this is about the right brightness. And here we are, as scientists there do, using whatever he used for an instrument. So.
Paul Lind has a question.
Go ahead.
Yes, is this Abel radius in an actual, is it a sphere out in space? And if so, how do you measure the distances to 18th magnitude galaxies?
Well, you start at the center, which is will be at the 10th brightest in the calculation that he had. And because all of the coordinates for the Abel galaxy clusters are tied to the brightest or the 10th brightest galaxy in the group. And then the radius is calculated. And then I think he just used the plates from the sky survey and scanned through based on that definition and counted up galaxies. Like I say, there are no official list for which ones they are.
But isn't it based on redshift at all? I mean, like,
Yes. Oh, I'm sorry. Yes, redshift is.
Numbers, those are physically associated, and the rest are just interlopers at different distances.
Oh, okay.
I all the fiber spectroscopy you get, redshifts are known way down 18 magnitude of all the galaxies.
Okay.
So
Hold
I
on.
think that it's just that.
That answers my question.
Yeah, that's just.
Hold on. I'll give you a peek of what's there, and then I got to get out of the way because there's other people kind of queued up to speak here. But I've got to, let me get there. Oh, I'm going to open up here, bring this over. I'm running on a Mac, which also runs Windows. Isn't that wonderful? All at the same time live. But I can get to this page a lot quicker this way and open up my shared folder, observing program. Come on. Don't hang on me now. I love playing with the beach ball. You're in a Windows program and you're getting a beach ball, which is a Mac. A Mac, hang on. It'll settle here in just a second. I think I can answer his question. Please. There we go. Okay. And open up this. All right, can you see that? Those are the three. Can you see those three charts?
Not yet. You'll need to share
Oh, I got to share the screen. Okay, I can do that. I got to bring Zoom back up. Share the desktop. Share. Did that do it?
Yep, you got it.
Okay, there are tables here. These are, by the way, from the NASA site, the NASA research on the Able galaxy clusters. We have the richness class, which talks about how many galaxies in each group. Okay, then we have the Able distance group, which is based on magnitude of the 10th brightest galaxy within the group. I'm going down to here, end of group 4, which starts out at 16.4, add 2, so the dimmest would be 18.4. There are 3 more groups, but I won't be able to see them from the backyard. There is another table that goes with it. When you were talking about the redshift, well, I thought it was in this table, but it's not. The redshift is there, and it's if you look at my sheets, I'll bring one up real quick. Close that. I put the redshift, for example, because it's actually something that is in the calculation into each one of the charts. And I'll go to here and I'll just pick this one. It doesn't matter. That's 2014, 2014, 2018. Here we go.
Yeah, we're not saying anything.
I know,
Okay.
but now you
That
are.
was me. Oh, here we go.
Well, unfortunately, I need to pick I'll pick one from the group 4. I'm sorry. That's an older observation. Index to images, group 4. There, these are the current. I'll pick this one. That's the current sheet. And you should be able to see my observation sheet on this now, right? Yes?
It's fine enough that it's hard to see.
Okay, over here on the left, I have technical data. And in the information about the galaxy, I list not only the coordinates, but the official magnitude, in this case, 16.1. And here is the redshift. And I make a notation just for clarity. This is a value calculated by NASA. The redshift for this galaxy, by the way, I should say it's the updated NASA calculation of the redshift, is 0.1248. And the radius on this is 24 arc minutes, meaning it's the diameter, or if you will, field of view needs to be like at least 48 minutes to be able to bring the whole thing in. And this particular image is 1 degree, 1.5 degree by 1 degree. So I make that, it's contained within that image. That's done with the 80 millimeter. So yes, redshift is a definite player. That would be part, I think, of the extended conversation if we do this as another program. Did that cover that adequately for now?
I think we got it.
Okay, gonna close that. With a little luck, I'll find the screen that says stop my share. You wouldn't believe how many screens I have open right now. Stop the share. Ta-da, that should do it.
Okay. Well, I tell you what, how about if
That was more than 5 minutes. I apologize.
I'm not worried about that. If these people are concerned about getting home that early, they can leave early. Okay. Let's see, where Steve. Yeah. I have my technical assistant here, my Tom Boston lookalike. Well, how about if you let Mike go? Yep. Next, because we were talking about the SAC lists. So I think Mike's gonna talk something about that.
I gotta sit up here.
Yeah,
That's the thing.
Well, you could
For people to
stand
see.
if you want.
Well,
And
and
just
I'll
tip it back so
open
they can
up
see your smiling
Lori's
face.
while I'm here. There's Lori's.
That's nice.
Yep. So. That's all yours.
Okay.
PowerPoint enough that-
Do you have the, yeah, down here? Okay. Big screen. Okay. All right. Well, good evening, everyone. So if I haven't met you, my name is Michael Poppery, SAC member now for 10 years. Okay, in 2012, a friend of mine named Jeremy Perez, lives up in Flagstaff, invited me to go observing out in the Kofa Range out in western Arizona. And as part of that observing group were such SAC luminaries as Mike Wiles and Chris Hanrahan and our very own Tom and Jen Palakis. And somehow I let them talk me into joining this group. And so 10 years later, I'm still on that journey. And what I wanted to do is talk about my continuing journey through the Herschel 400 list and how that's been going. David mentioned these observing lists that we have in these clubs, and they are a fantastic way to help focus your efforts for getting out there and observing instead of just kind of going randomly or wondering what it is you're going to look at tonight or something like that.
We're doing the Messier one more time.
Exactly. Yes, exactly. Exactly. So anyway, the H400 list is a subset of a number of different lists that were started to be compiled, some by William Herschel in the 1700s and by some other folks. And then, of course, compiled into the NGC catalog in the 1880s. And this list, the H400 is basically considered to be a next step after doing some of the maybe less arduous lists, such as the Messier 110 and things like that. So if you're looking for more than just the brighter Messier objects, it's a good way to jump into some other objects as well. So it was actually first developed by members of the Ancient City Astronomy Club in 1980 in St. Augustine, Florida. And they looked at a lot of what was out there and they said, hey, some of these objects are really great. Let's kind of cull it down. Why they chose 400, I really don't know. It might be, someone might know that, but I'm not really sure. But they came up with 400 of essentially Herschel's best objects and called it the H400 list. And it does form the basis for the Astronomical League's viewing list and their Herschel 400 Club. So that's another source for organized observing lists as well as the Astronomical League. SAC has its own published list called the Herschel 400 list. And I noticed that the word Herschel is just misspelled for some reason on there. It was originally compiled by A.J. Crayon and the late Steve Coe. And obviously is available on the webpage as David showed us. Also, an interesting thing on there is, we okay?
I'm not sure if,
Are we broadcasting?
I'm not sure we're broadcasting your slides.
Oh,
I don't see my. Okay. Let me.
I have not any.
Are you seeing, are you not seeing anything, David?
oh, nothing's coming up on sharing screen.
Okay, let's go to. Are you seeing anything now, David?
I see Tom Curry has started sharing his screen.
Are you seeing any,
No slides.
no
No
slides? Oh, I wonder what
slides.
that's. Okay. Okay, next month we will not be Zooming.
Display settings.
Yeah, where are we?
I don't know.
Okay.
Slot, what was that?
Tom, are you,
The screen sharing is paused. It says in
Where-
yellow. Is there a-
we're down,
At the top.
Oh, up there. We don't see that on here. See, we don't, your screen sharing is paused.
where do you see?
Up there, look on the
Oh,
screen
okay.
over there.
Is there a,
We don't see that on here.
okay, I need to get into then, I'll minimize yours. And go down to,
Zoom.
yeah. Okay, I don't know why this,
What is it he's trying to bring up? The Herschel list?
no,
No, no, no, no.
no, we're just trying to get back to the Zoom screen. And I'm not sure why I'm not,
Your PowerPoint's in presentation mode, it's a different screen than you're sharing.
No, that could be it. That could be it.
yeah, but, okay.
When I went into presentation mode, it might have
Okay, I
done.
need to see where these little sons of bitches, pardon me. But- Yeah, do we have an expert back in anywhere? Help.
A Zoom expert?
Yeah, but that doesn't mean anything about Zoom, yeah. Zoom is not computer science. Okay, it's, why aren't we?
Well, this is gonna be important for everybody else.
What are the buttons that are up on the below?
Yeah, we don't, I mean,
Well,
that's the thing,
so
I'm not
do
getting,
Do this, go into my presentation and cancel,
oh, wait a second, here we go. Is that it?
no. So
Okay.
I think what happened was when I put it in presentation mode, it might have screwed things up. So,
Need to,
so that's not in presentation.
so it's, is it in, where is the,
Presentation mode
Right
is that
here?
one there.
yeah, the second one here?
Yeah, that one there. That's presentation mode.
Okay.
That's what
Learn
I
how to
was in.
Share the screen. I've
Pardon
never
me?
seen that before. Something about your screen sharing.
Yeah, well, that, it's,
I know. And then.
For some reason,
we
we're
can't
not-
get the mouse to, so.
That's what I'm saying.
What is this?
share.
No, that's, I don't think that's. No.
I'm just trying to get all of these up here now.
I don't
Okay.
think it has anything to do with that. Yeah, that's
So-
right.
Come down to that, and are we over here?
No, that's just your regular.
So this is,
You don't have to Zoom.
yeah, I mean, I don't know what happened with,
You're on the, that's the Zoom web page, right?
yeah, and
But
it's,
the
I don't know.
Zoom app is this thing down here.
Yes.
Yeah.
Click that.
Okay,
So meeting control.
okay,
Zoom cloud meeting.
yeah,
So that's just that.
it's just,
Stop the share. Well, it's amazing that you're not seeing the same thing.
Yeah, I know,
I've never
I
seen
know.
that
That's
before.
what,
it's,
so strange.
it's just me. I have bad electronics in my body that are affecting everything. Okay, where can we? Okay. It's got to be,
Well, there's two things open here, right?
what is, and this was,
No, I still think there's an issue with,
it's not questions, I can barely read. I need to dig out my magnifying glass to see.
one is people asking questions.
They're probably asking
So-
questions now, we just can't see them. Oh, is this the paused up here? Yeah, hit that up.
Paused. There, that brought up a menu.
Okay, now click on that.
You gotta move it over. This is bullshit.
Yeah, just,
Well, how do I get rid of that?
yeah, minimize it.
Minimize it. Sign in again. Steve,
What?
Not signed in.
No.
Sync is paused. Well, that's not right.
Sync is paused.
Pause. So you click that and all it did was pop that down.
It just popped that menu up, yeah. But there's.
Well, it's got me talking, but it doesn't have,
Nothing comes up when you do meeting.
Three dots over the, oh, that just brings up websites or something.
Yeah,
Never mind. Yeah, I've never used the web interface, so I always get the app.
well, I know, but we got the app open, and that's what I don't. Well, what do you say we maybe kill the PowerPoint thing? and
That's
see
what I
if
was
we
thinking,
get-
at least do that.
See, we got two things. This is in theater mode, and this is in.
Oh, this is, okay, here we go.
All right,
Now,
we're back to this.
okay.
So now,
Screen sharing is stopped. You can hit OK.
That's fine.
Okay.
that.
Now, we need to minimize that and, oh, yeah, share up at the bottom. Go back to in here. Just go into, just on here. Yeah,
minimized
now
it.
hit the corner, right?
This guy?
Yeah.
Okay.
Now go down to share the green. Yeah, now you should be able to bring that up.
Okay, that's Lori's.
Oh, okay.
Because I canceled mine.
Okay.
Well, I know.
Okay, so go ahead and should be able to open yours. Now that you're in the share screen, open this and it should pop up. And
I should be able to open recent. Yeah, here it is.
yeah,
here.
let's try. Now drop to the bottom and see if the
Go back to Zoom.
slide down.
Back to Zoom.
Here, over here.
And now share screen from the, oh, unless you're already in that.
All right,
It
it
looks like
didn't-
you're already in it. Now go to
It didn't
yours.
bring it up though. Mine's not in.
What the hell is that?
Optimize video clips. Wow. I don't know what to tell you. Do I have to do something here where I need to share this?
Yeah, you have to share this,
But not up here. is
but
it?
what you bring it up on the laptop screen, and then you should be able to go into hit share, and then now go.
I don't think that's right. That's not the same sharing as Zoom sharing.
Oh, okay.
I
Okay.
really don't think it is.
Okay. Now go down to Zoom again and see if it's now up into here. No, it still didn't come up. What? What
Mine
in the
doesn't.
world?
Lori's is here.
What in the world?
All right, let's. So we are up there. We're seeing it. Okay,
Yeah.
well, let's do this because we're really blowing
Okay.
through time here. I'm gonna kill mine here. All right.
Well, wait a second.
now-
Wait a second. Do that again,
Well, let's.
because I thought you were on the screen.
Lori, where's Lori?
Is the desktop one of your options to share? I guess that's not it. There's just too much stuff.
Yeah, it might be. Okay.
You are screen sharing. You're screen sharing. We have it now.
Yeah. Okay.
Hey, Lori, do you want to
There
go?
you go. You did it.
Well, we're
Apparently, we can get yours working. I don't know.
okay. We'll do yours and then we'll do Paul's.
Anyway,
Okay. Okay, for you at home that are experiencing this, we are having a conundrum here. I will let Lori have the podium. Yes, go ahead. I'll let you run it. Down to the bottom right.
What am I hitting?
Green thingy.
This one or which one?
Yeah, it's one of those Need a friggin'
Yeah,
magnifying
usually
glass
look
every time I
for-
look at these things.
Oh, touch something. Yeah, touchy screen.
Yeah,
Okay, no, that's not gonna work. I gotta start with that one. Okay,
okay, then,
is it that little desk thing?
yep, right there, should be. Yay.
Okay.
Now, are they seeing?
I would presume that they are. David? David, can you see that?
Yes, Tom, I can see it. Yes, Tom, I can see it.
David, can you see that on the screen?
Yes.
Okay, thank you very much. Okay, okay, appreciate that.
Sorry, Michael.
We'll try again. We've got time.
Okay, okay.
Okay.
So there were two blondes sitting on a bench in Las Vegas looking at the moon. And one blonde says to the other blonde, "So what do you think's farther away, the moon or Florida?" And the other blonde says, "Well, duh, you can see the moon."
Yeah.
So you might notice that I am blonde. So I'm lowering your expectations at this point so that anything I say above that expectation will sound brilliant. So that was the plan. Okay.
You might want to stand close enough. That they can
Okay. Okay, so in 2017, we had this object enter the solar system. It came from outside the solar system. And this is an artist rendition of what they thought it might look like right up front, but things changed over time. It was only seen time to take pictures of it, to send spacecraft, to chase it. So it was traveling so fast that that's how they knew it came from outside the solar system. So it was originally classified as a comet. Observations revealed no signs of cometary activity until after it slingshotted past the sun on September of 2017 at a blistering speed of 196,000 miles per hour. It was briefly classified as an asteroid until new measurements found that it was accelerating slightly, a sign that it behaves more like a comet. So this is the actual picture that we got of it. So you can tell that the artist took a lot of advantage in their drawing. So this is deep, this very deep combined image shows the interstellar object. They called it Oumuamua. At the center of the image, it's surrounded by the trails of faint stars that are smeared as the telescope's tracking the moving object. Okay, so what's unusual about this thing? So Oumuamua varies in brightness by a factor of 10 as it spins on its axis every 7.3 hours. No known asteroid or comet from outside our solar or from our solar system varies so widely in brightness with such large ratio between length and width. So they know the size of it by its reflectivity. The most elongated objects we have seen to date are no more than 3 times longer than they are wide. So Oumuamua was a Hawaiian name because it was first found by pan stars in Hawaii, meaning a messenger arriving first, a bar arriving first. Okay, so here's the really strange thing about it. Here's how it came into our solar system, slingshotted around the sun, and then exited. When things slingshot around a massive object, they have a gravity that sits. That's why we send spacecraft around other planets to pick up speed when they're going out into space. But this didn't behave that way. They took that in. This is where it should have been, but this is what they observed. It got 100,000 kilometers further than it should have. In other words, it picked up speed more than was anticipated as it went around the sun. So they're very interested in this. Of course, SETI started listening and seeing if there's some kind of signal, listen to it for 60 hours. The Green Bay Radio Observatory monitored the object in 4 band frequencies. That's what they heard. Silence. So imagination started kicking in here. What's this thing? Where did it come from? What's going on? All these theories popped up. So some said, oh, it's got to be a comet because comets will pick up speed as they're outgassing. But as the Spitzer Space Telescope was observing this thing, it didn't have emissions coming off of it. And it's very sensitive. It's what it would have seen if there was CO2 or CO outgassing. Asteroid, we've never seen an asteroid in nature that's that length to width ratio. So that maybe it's a hydrogen comet, and Spitzer wouldn't pick up the emissions from hydrogen. Hydrogen's a light gas and would have instantly evaporated that close to the sun. So none of these theories have really panned out. We still have a lot of questions. So you may have heard of Avi Loeb. And so he is an Israeli scientist currently working for Harvard, and he had some extra ideas, extraterrestrial ideas. And some of you may have read his book. Really good book and really fun to read. A lot of science behind it. He's not speculating without evidence and without, some background information there. So he feels like, well, maybe, just maybe, this is some debris from another civilization, an escape piece of something that is very thin, that is very wide, that's very shiny as it rotates, and that it's light enough that the rays or the radiation from the sun is what pushed it to make it speed up as it left orbit. So it's another kind of idea that we can't prove. It would take, more objects coming in the solar system that are similar to be able to track them for longer to get more information. But the idea is we have to have open minds about things in astronomy. It's an evolving science. I tell my kids at school, I said, if you go into a math class or a chemistry, because we've advanced enough that those laws and rules are the same, astronomy changes every day. Every day something new is coming up. So just to make my point there, 100 years ago, the telescopes of the time could see one of these beautiful spiral, what they call spiral nebula. They didn't know what they were. They didn't know how far away they were. They just know they could see them with the telescopes. So there's actually a big debate about this, about what these objects were in the sky. With Harlow Shapley and Curtis, they had this big debate in, it was 1920. And they were each right about some things or wrong about some things. Shapley made the correct deduction that the sun was not at the center of the galaxy and that the galaxy was much larger than previously thought. He thought it was 300 light years in diameter. He used variable stars for his measurements and globular clusters for his data. So he was correct that we aren't in the center of the galaxy, and he figured that out by the placement of these globular clusters. But 300,000, and he thought these spiral nebula were actually within the Milky Way. Curtis was different. Curtis had a different idea. He argued convincingly that the spiral nebula were external galaxies based on many novae seen in the Andromeda galaxy. He reasoned that so many novae were observed per galaxy in a particular amount of time, so Andromeda must be separate. Our own galaxy is just one of the many island universes. He thought the Milky Way was 20,000 light years across. So they're both right about some things and wrong about some things.
Oh, excuse me, Laura, you're fading away. You're fading away there.
So just to make my point still.
Closer to the microphone.
I'm fading away.
Yeah.
I think I'm one of the witches in Oz and they put water on me. What? Can you hear me now? If I'm closer?
Microphone.
Hello, can you hear me now?
Jack, can you hear us now?
Volume has.
Are we losing our audio?
Just read the slides. You should have come in person.
Yeah. Get you all sick.
It's been this way.
Lori,
Sorry.
Lori,
talking as loud as my little wussy voice goes.
Lori, I hear you
Okay.
crying out here.
Yes.
Oh, okay, it's Jack.
It's just Jack.
Jack's
Jack,
sick.
go
His ears
find
are
that
bleeding out.
little seashell and stick it in your ear. Okay, all right. So the first exoplanet that we actually were sure was an exoplanet, 1995. That's hardly any time ago to say, that the first one you've ever found. Today, we just passed a couple months ago the 5,000 mark of confirmed planets. So confirmed is special because we get a lot of data back from spacecraft, from Kepler, and from tests showing us what they think is a planet, but it has to be confirmed by a second method to actually put the tally mark up. They have to make sure that that's correct. So TESS has found 209 of them. It has more to check out, another 5,600. So we're moving along. Science is really moving on. So here's Frank Drake. So Frank Drake is called the father of SETI, which is the search for extraterrestrial intelligence. So in 1961, he was holding a conference, getting together a whole bunch of scientists, and he wanted to get excitement up about looking for extraterrestrial life. So he decided that he would come up with a bunch of themes for the conference, different topics to speak about. And then he's sitting there making his list of topics. He goes, wait, I think I can put this into a formula. And so he did. I'm going to skip that because we're short on time. I'll skip some things. Okay, so here's his formula. He put all the topics he wanted to talk about in a row. So the N stands for how many intelligent communicating civilizations are out there. How many? How can we calculate how many there are? So this stands for how many stars are being born each year. We've since figured out that that's about 7 in our galaxy. So how many of those stars that are born actually have planets around them? Well, we've also calculated that pretty accurately at this point. And it's 1 planet for every star you see in the sky. Now that doesn't mean every star has one, that means the average. Yeah.
Then that's what we see with our mere little telescopes that we just started using.
They cannot see them all, but they can guesstimate how many more there are by what we can see. And the reason is some of the methods, I think I showed them.
I'm trying to say that there's more than what we see, because we don't see a lot more than what we do.
We aren't seeing all that they're saying are there. Let's put it that way. But our methods are getting better, but I'll show you how we figure that out in just a second. So, but like with our sun, we've got 8 planets around it. So maybe the next 7 stars will have none. So it's an average, like 1 star, 1 planet. Okay, so, but how many of those planets are Earth-like? Well, have we been able to find that they're Earth-like? But there are some, we think there are some. And of those, how many develop life? And of those that develop life, how many of those develop intelligent life? Difference between a microbe and intelligent life. And then how many of those can communicate? So we're moving up the scale here, and obviously the numbers will get smaller and smaller and smaller as we go through the formula. The last one is L for how long does a civilization last? How long can it actually communicate into space? Something we could pick up. All right, so what kind of life would we be looking for in the cosmos? Something similar to us. Because if we're looking for silicon life forms or other kinds of life forms, it's kind of science fiction. They may exist, but since we don't know for a fact they do, or that we know this kind of life exists, we know that carbon-based life forms exist. So that's what we would be looking for. To the terms just really quickly, might not be that quick, but we'll go through them anyway. Okay. It is safe to assume that the other alien life will similarly depend on the energy of a host star. In the equation, we call this R star. And That says something under there. So how many stars do you think form in a galaxy? Well, we've calculated at this point is 7. Okay, so the right kind of star to look for life. So this is the Hertzsprung-Russell diagram. They each came up with this independently in 2 different countries, but they took a bunch of data of all the stars that they had data for, and they kind of plugged it into a chart and came up with this, and it's very useful. So up here we have the giants. This is when stars are getting to the end of their lifetime. They're no longer burning hydrogen in their core, so they're inflating. Down here we have the white dwarfs that are dead stars from here. This diagonal line, those are main sequence stars. These are the stars that are balanced. The radiation pressure from inside, from the nuclear fusion, is pushing out, and the gravity's pulling in, and they're balanced. So they're stable stars, and stars spend 90% of their lifetime on here, and 90% of the stars in the sky are on that line. So if we choose a star up here that is on the main sequence and it's in hydrostatic equilibrium, their lifetimes are really short. These great big stars down here that are the tiny red dwarfs, which we find planets around, they are a little bit unstable. I used to think, oh, we'll just move the planet in, it'll get warm enough, we'll have lots of water. But when I talked to somebody from ASU that was studying red dwarf stars, she said, no, they're unstable, they're erratic, they give off, brighter, dimmer, so they're not really perfect either. So of course, right in here, right where our sun is, that's the size we'd be looking for. They live a long time and they're stable. This isn't good. Okay. Wow, my background really faded out. Okay, so we're going to FP here. FP is how many of those stars actually have planets, and how do we find those planets? So these are the methods we can use for finding planets up there, and the 2 main ones are radial velocity and transit. You'll notice very small numbers in any other method. So this was the first Kepler mission, who is now dead, but was in space for a long time. Look how many stars it looked at, how many planets are confirmed from that mission. So amazing spacecraft. So we now have a different one, but the way it used, yeah, I would have so changed my background.
Yeah, printing white on a white background.
It was
not a good
gray
idea.
at home.
Yeah.
It was gray. Okay, I'm going to make it up as I go then. All right, so this is the transit method. So this is the mini eclipse. So this is where it comes into when we can't always tell if it has a planet, because look at the angle. So the planet has to circle in front of it, block some of the starlight to make a little dip in the light, and that's how Kepler and Tess figured out there were planets up there. All right, so if we were to take that system where the planet's going this way, from our perspective, we're not going to see it. It's not blocking anything. Okay. All right, so from transits, we can use the size of the star and what percentage of the light from its block to calculate the planet's multiple radius. So from this, we can figure out the size of the star. We can figure out how much light it's blocking, and we get the radius of the planet, and that's very useful to us. So this is what Tess is taking a picture of. I did prepare an hour thing.
That's
So
okay.
no, it's not, because so we've got, who else come? Yeah, both these 2. Who else? Anybody else besides these 2?
Well, we got Paul.
Paul's going. Okay, so I'm going to skip the videos. But this is a little video on Tess and how it's taking pictures of the sky, and really amazing. You can go home and watch it on YouTube. But it has 4 big cameras. Kepler was like the little bear compared to Big Bear. This one is like massive in the sky, like crazy. So Tess is going to be very, very useful to us. So this is what more of a real transit looks like. So a light curve. So here's 100% of the starlight when we look at a star. Look how much is dimmed of it. Only 0.4% So it looks like a big dip, but the scale is cut off at that point. So this is going to be a really big planet, a Jupiter-sized planet that cuts off that much light right there. So that one is a little tiny planet. All right, so our second method that's the main method is the radial velocity method or the wobble method. So it's another way where we use redshift and blue shift. So stars and planets don't orbit each other per se, they orbit the center of mass. So in this particular instance, there's the center of mass, so the star's orbiting it because it's being tugged on by that planet. So we aren't going to look at the planet, we can't see the planet, the star's way too big and bright, but we can see how the star wobbles. We can see that the star is moving away from us, and we can tell that it's moving towards us. And from that, we can calculate the mass of that planet. So now we have the radius of it, and we have the mass. Very useful. All right, so there's sort of a demonstration of how that works. So in this particular case, the center of mass is inside that star. So it's still wobbling, but it's not outside of it. And our solar system, our center of mass is inside the sun. The sun does this kind of thing, being tugged on by the 8 planets. All right, so once we have the radius, we have the mass, we can calculate volume, and then we can calculate density. My students love doing the calculations. Yes, no. Okay, so from that, we can figure out what the density is. We can tell whether it's a gas planet, whether it's ice planet, whether it's rock, whether it's metal, but the reality kind of figure that out, right?
Usually what?
A mixture of those things. So for instance, Jupiter would probably have a rocky core, but a gas outside, that type of thing. All right, so then we're going to move on to how many of those planets are Earth-like? So Earth-like, we need to have liquid water. Liquid water for life on this planet is essential for every form of life. Okay, we also would need moderate temperatures and atmosphere. So then we figure out how many have that. So we look at just planets in our solar system. You know, we look at Jupiter, we look at Pluto, Mars, the surface of Mars, we look at Venus. None of those are even remotely habitable for life forms like we're used to. They're out. So planets up there are like that too. They're going to be extremes of one sort or the other. So to have a communicating civilization, we first have to find ones that can support life at all. So our next term with life. So then you have to kind of define life or what it's like. So this, for our purposes, the technical thing is it has order, it's capable of reproduction, growth and development, it has a metabolism, in other words, it uses a fuel of some sort, response to environment and evolutionary adaptation. Big whole thing. All right, so on Earth, we have big life, but then we also have microbial life. So we have 2 different ones, and they're different, and what they need to sustain them out in the world are different. So these are the microbes. We have a whole bunch of them that we term extremophiles. We literally can find life on almost any spot on the entire planet. You can find them in acid rivers. You can find them in hot pots of Yellowstone Park. You can find them in bases in a certain amount of radiation. You can find them in salt water. So life loves to be on planet Earth. And so looking for these out in space, this is what they look for, evidence of this type of thing on Mars with their rovers and stuff. They're looking for evidence of past life, but it would be past microbial life. So that we're not interested in because they're just bugs and they don't talk to us. We want to look at things that talk to us. All right, so large life are all tolerance for temperature and atmospheric changes. So things that we would need in a planet, and I'm basing this again on planet Earth, what we have that supports life here, we're in the habitable zone. And all that means is, the Goldilocks zone, the habitable zone, you hear this over and over again. What that means is we simply need liquid water. If it's frozen solid, that doesn't help us. If it evaporates away, that doesn't help us. We need liquid water. So that's why the distance from the star is so important. All right, so we need the right kind of star. We need a star that's going to live a long time. How long do you think it was till the first life showed up on our planet? That we had the first evidence of any kind of life on planet Earth?
4.6 billion years.
Any kind of life, not just humans.
Oh, billion.
Okay. It's about 1.5 billion years after it cooled off and we got oceans and stuff. We have the first evidence of microbes. So that's life. But to get from that little tiny bug to become a human civilization where we can communicate with space, that's another almost 3.5 billion years. So we need a star that will live long enough for this track to take place. Now, planet Earth, we had 5 major extinctions. We think we're in number 6 right now. So if but for our purposes, we'll think we need a long living star. We also need a star that's maybe not in this, well, I think I have, oh, there it is, in the right place. If we had a star in the center where all these stars are crammed together, we're going to get so much radiation that it would be harmful for life. And we wouldn't be getting any sleep because you'd have to wear those things. So we need shield from radiation. We need a magnetic field that protects us from harmful rays of the sun. We need an atmosphere that also, we need an atmosphere. We just need an atmosphere. Yeah, to block the UV rays that are coming from the sun, because we only get just a little bit of that sunburns our noses, but the really harmful ones that don't come through our atmosphere. We need the right minerals, Tron plus phosphorus and sulfur. If those aren't on the planet, then we wouldn't be able to create life as we know it. We would. Plate tectonics and carbon cycle. Why are those so important? Well, first of all, the carbon cycle. If you look at planet Venus and you see how it's just got that thick atmosphere, that's mostly carbon dioxide. So Earth kind of started out with, well, in fact, Earth has as much carbon on planet Earth as Venus has. It's only ours is trapped in the rocks. So if we didn't have ground, we would get, in fact, that's why we don't want to dig it up in fossil fuels and put it back in the air. It's because nature took care of us and put it underground so we could breathe and so the planet wouldn't get too hot, and humans are undoing that. So plate tectonics help us with that carbon cycle to keep that trapped. A protected planet is just kind of a bonus, but you've probably seen pictures of Jupiter where comets have hit it and it's bruised. It rips them apart and it gets hit like 22 times. Boom, 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 boom. Some of those things could hit us if Jupiter's gravity hadn't kind of pulled it in. So it kind of keeps us from getting hit as often as we might. A large moon to stabilize the planet is a bonus that we have as well. So Mars, for instance, Mars has 2 little bitty moons, Phobos and Deimos. Doesn't matter, it doesn't help Mars at all. There isn't enough gravity, isn't enough, and they're just captured asteroids. So the moon, though, the moon stabilizes the axial tilt of planet Earth. So it stays at that 23.5 degrees. Mars, over the years, tips down and back up again. Can you imagine what that will do to our climate on planet Earth if our axial tilt did this over the years? Okay, atmosphere, obviously we need that to protect us from gamma rays, protects us from X-rays, from most UV rays. So very helpful, as well as we'd like to breathe. Breathing's good, okay. All right, so intelligent life, FL, down here, developing into intelligent life. So we can define intelligent life in many different ways, but these are some of the ways: tool use, social living, language, agriculture, altruism, trade and barter, global environmental change, music, art, culture, superstition, abstraction, self-awareness, and deception. So a bunch of things that we humans use. And this was another little video clip that I'm going to skip of very smart animals and things that they do that show intelligence. But the evolutionary thing that happened, no nervous systems to bigger brains and very complicated nervous systems. By giving that adds to the intelligence of an animal and allows us to develop. Okay, so if we want to find alien life, it must be detectable. On Earth, the only civilization of intelligent life that communicates with the stars are humans. We live in societies that use technology. We hypothesized that aliens would need to be organized into civilizations and have technology in order to be detectable, although this might not be necessary. So now we're looking for communicating people. So doing his work with SETI, but he actually did it a lot farther back in time. 1974, he made a transmission of this message to the globular cluster M13. The message was sent in simple binary coding consisting of zeros and ones, then decoded. The message produced this image, but in black and white. So he's telling the aliens about our DNA, total human population, typical height of a human, solar system with Earth's position, etc. We didn't hear anything back. Okay, so then the next message, we start getting messages we send out on the Pioneer. When I show this slide in my class, I dress the people. I put little clouds over their private parts, but you're a mature audience, so we'll just let it go. All right, so then we have showing our solar system, we have hydrogen molecules, so they send us out into space. And then finally we send out the golden record, which is actually copper record painted gold. But this one with pictures and with a needle to play the record and sounds from all over the world, I think that's kind of awesome. I'd actually like to have one of these at my house. And then I was going to show you this clip about what's on the record. Okay.
Chuck Berry.
Chuck Berry?
Yeah.
I think you're right. I think you're right. Yeah. Okay. So whether an alien civilization is detectable will depend on how long it exists. A long-lived civilization is more likely to be detectable than a short-lived. How many years do you think a civilization needs to be communicating to be detectable? So down here where you can't see, this is a bright green L for how long things last, the last term in the equation. So how long can a civilization last? I keep telling my students, all it takes is an idiot in the White House. And it's all over. And I won't make any more comments on that because we're going to have a big political debate here. But we had a close call until it. All right. So Washington Post in 2015 came up with some things that could destroy the world. So this is, I'm not going to end on this sad note, just know there's hope at the end of this. All right, so artificial intelligence, they saw this as sort of a danger. That, you know, we see this in movies where the machines take over the world. That was the thought. Synthetic biology, when we start goofing up with, messing with biology and chromosomes and creating things that aren't nature, maybe. Climate change, we know this is an issue. We're seeing it every day. And from that, we see extreme weather. We've seen extreme weather, fires and crop failures. Nanotechnology gone bad. Asteroid impact, it's happened before too. Global pandemic. Now, we escaped the last one, but it could be worse. It could have been worse than it was. All right, so the thing is we don't have to destroy the world to have communication go quiet. So while commercial radio broadcasts began about 100 years ago, these early transmissions use frequencies that are either mopped up by the atmosphere or drowned out by radio emission from the sun. In contrast, military radar transmissions set up during the Cold War to detect incoming ballistic missiles have the power and frequency characteristics to be detected over hundreds of light years and have already broadcast our existence to any aliens within 60 light years of Earth. So some things are broadcast and some things aren't. Mitch hates it. He won't even be in the house when it's on. So I watch it when he's gone and I'm sick. So in Galaxy Quest, the aliens come to Earth because they think the Earthlings can help them with their mortal enemies out in space. And they think that everything they've seen on TV that was broadcast in space was real. And when they are confronted about it, they said, you don't really think like Gilligan's Island is real. And they go, blasting into space. So the galaxy in the image is a reconstruction of the Milky Way. If it were 110,000 light years in diameter, its itsy bitsy blue dot is how far our radio signals have traveled from Earth, about a diameter of 200 light years. See that dot? It's smaller than my red dot. That's how far that we have transmitted our signals so far. So now we are also not broadcasting into space like we originally were. Now we've got satellites. And so when we send messages, they go to satellites, they come back down. So they're not going off into alien territory like we used to. So this civilization of humans has probably gone pretty much radio quiet, even though we haven't had the idiot in the White House yet. So, okay. The equation is currently unsolvable because we do know the values of most. We do not know the values of most of the parameters. The unknowns help direct our search. There were a couple of scientists that kind of revisited this equation, and they came up with some actual numbers. They said, yeah, stars with planets, 1 planet for every star. The number of planets that are Earth-like that could support life, 1 in 5. I think that's very optimistic. Nice. Chance of technological civilization evolving on a habitable planet, 1 in 60 billion. Likely this has happened in the Milky Way. In the observable universe, 10 billion planets with technology producing life, but many of those could be extinct by now. So they could be up there. And hopefully someday we'll find out. So I just found a couple of things to Okay, that's it. Thank you.
You, Lori, that was delightful.
I just don't see any hope. I'm gonna be dead long before that, so the hell with it. I'm not worried. Why don't we take a break while we try to load, unload, get Paul's ATM report in and get Tom up. See who else was going to present. So what? Oh, okay. Josh left. Okay. Okie doke. Let's see. Okie doke. Let's get down here. Okay. Let's see. How do we? For those of you at home, I'm going to pause the recording